Welcome, cosmic travelers, to the Cosmic Atlas, your guide through the greatest mysteries our universe has to offer. If you're joining us for the first time tonight, I'm so glad you found your way here. And if you're returning, welcome back. It's wonderful to have you with us once again. Before we begin tonight's extraordinary journey, I'd like to ask a small favor. If you find yourself drawn into the story we're about to tell, if the mysteries we explore spark something inside you, please take a moment to subscribe to the Cosmic Atlas. Your support helps us continue creating these journeys through the cosmos. And if you'd like, press that like button. It helps others discover these stories too. Sharing with someone you think might enjoy this exploration means the world to us. Now, let's talk about where we're going tonight. 17 miles beneath the border of Switzerland and France, there exists a machine unlike anything humanity has ever constructed. A circular tunnel, carved through ancient rock, stretches underground for 27 kilometers. Within that tunnel, particles smaller than atoms race at 99.9999%, the speed of light. They're moving so fast that from their perspective, time itself nearly stops. This is the Large Hadron Collider, and tonight we're going to explore what happens there and why it matters to every single atom in your body. What you're about to hear isn't science fiction. Every word is grounded in verified research, in peer-reviewed discoveries, in the work of thousands of brilliant minds who have dedicated their lives to answering humanity's oldest questions. What is everything made of? Where did it come from? And why does anything exist at all? The discoveries made at the LHC have already changed our understanding of reality. The Higgs boson, found in 2012, explained why particles have mass, solving a mystery that had puzzled physicists for half a century. Exotic particles, combinations of quarks that should not exist according to older theories, have been discovered. Antimatter has been weighed by gravity for the first time. Quantum entanglement has been observed at energies that existed only in the first microsecond after the Big Bang. But perhaps more importantly, there are mysteries still unsolved. Dark matter, which makes up 85% of all matter in the universe, remains invisible to us. The matter-antimatter asymmetry, why there's anything left in the universe at all, rather than having annihilated into pure energy, has no complete explanation, and strange anomalies keep appearing in the data. Tiny cracks that suggest our understanding is incomplete. Tonight, we'll journey through all of it. We'll descend into that tunnel together. Watch protons collide at temperatures hotter than the core of stars, and discover what those collisions reveal. We'll explore the Higgs boson and the question it raises about whether our universe is stable or balanced on the edge of catastrophic decay. We'll meet antimatter, discuss why it falls down instead of up, and confront the unsettling question of why the universe chose matter over antimatter. In the first place, we'll talk about exotic particles with names like pentaquarks and tetraquarks, particles that exist for less than a trillionth of a second, but tell us volumes about the strong nuclear force. We'll explore the quark-gluon plasma, a state of matter so hot and dense it hasn't existed naturally since the universe was a microsecond old. We'll examine the search for dark matter, for hidden forces, for anything that might crack open the standard model and reveal what lies beyond. And we'll do all of this in a way that lets you rest. This is a story meant to be absorbed slowly, like starlight filtering through a calm night. The details are here for those who want them, but the narrative will carry you even if you drift. There's no test at the end, no pressure to remember every name or number, just the invitation to explore. The scientists at CERN aren't just smashing particles together for the sake of it. They're reading the universe's source code. They're investigating the rules written into reality at the smallest scales, rules that ultimately govern everything from the fusion burning in distant stars to the neurons firing in your mind right now. So settle in. Get comfortable. Let the gentle rhythm of this story carry you. Whether you're here to learn, to drift into sleep, or simply to marvel at what humanity has accomplished, you're exactly where you need to be. Let's begin our journey. 17 miles beneath the surface, to the place where physicists are unraveling reality itself. Imagine standing in a tunnel so large you could drive a truck through it. The walls are smooth concrete, curving gently away from you in both directions. But this isn't just any tunnel. This is a cathedral for science, a circular monument to human curiosity that stretches 17 miles around, passing beneath farmland, villages, and forests on the border between Switzerland and France. People live their ordinary lives directly above it. They tend their gardens, drive to work, walk their dogs along country roads. Most have no idea that 100 meters beneath their feet, protons are screaming through an ultra-high vacuum at speeds so close to light speed that the difference is almost meaningless. If you could somehow watch one of these protons, it would complete the entire 17-mile loop 11,245 times in a single second. The Large Hadron Collider is the largest machine ever built by human hands. But calling it a machine feels inadequate. It's more like an organism, a living system with thousands of interdependent parts, all working together to accomplish something extraordinary, recreating the conditions that existed when the universe was less than a trillionth of a second old. The tunnel itself wasn't dug specifically for the LHC. It was originally constructed in the 1980s for an earlier machine, the Large Electron Positron Collider. When that experiment concluded, CERN repurposed the tunnel, installing an entirely new system, one capable of accelerating protons to energies never before achieved on Earth, lining the tunnel. Walls are 1,232 superconducting dipole magnets. Each one weighs 35 tons. Each one is nearly 15 meters long. Together, they contain enough niobium titanium wire to wrap around Earth's equator twice. These magnets have one critical job. They bend the path of particles that would otherwise fly straight into the rock walls and disappear. But here's where the engineering becomes almost unbelievable. To make those magnets function, they must be cooled to minus 456 degrees Fahrenheit. That's minus 271 degrees Celsius. To put that in perspective, the coldest natural temperature ever recorded on Earth was minus 128 degrees Fahrenheit in Antarctica. The coldest regions of outer space, far from any star, hover around minus 454 degrees. The LHC operates colder than the vast majority of the universe. Why such extreme cold? Because at that temperature, certain metals become superconductors. They lose all electrical resistance. Current flows through them without generating heat, without losing energy. This allows the magnets to produce magnetic fields, powerful enough to bend particles moving at near light speed, something a normal magnet could never do without melting. Achieving this cold requires 96 tons of liquid helium. The helium circulates continuously through the system, a river of cryogenic fluid keeping the magnets frozen. The system is astonishingly fragile. A single degree of warming in the wrong place and superconductivity is lost. The current would generate heat. The heat would cause more warming. The feedback loop would cascade in seconds. In 2008, exactly that happened. During the initial startup, a faulty electrical connection sparked. That spark heated a small section of the machine. The heat vaporized the helium. Helium, when it vaporizes, expands explosively. The pressure wave ripped vacuum pipes from their mountings and damaged over 50 magnets. It took 14 months and tens of millions of dollars to repair. The lesson was learned. When operating at such extremes, even the tiniest flaw has massive consequences. But when everything works, when the cold holds, and the magnets fire and the beams stay aligned, something beautiful happens. 2 beams of protons travel in opposite directions through the ring. They don't travel through air. They travel through a vacuum more complete than outer space. Just 10 to the minus 11 atmospheres of pressure. If even a stray molecule wandered into the beam path, collisions would scatter the protons and ruin the experiment. Each beam contains billions of protons organized into bunches. The bunches are spaced precisely, timed so they meet at specific points around the ring. Those points are where the detectors wait, massive machines surrounding the collision zones, ready to capture every fragment of energy released when protons smash together. The protons don't start fast. They begin as simple hydrogen atoms, pulled from an ordinary gas bottle, the same hydrogen that powers stars. The electrons are stripped away, leaving bare protons. Then the acceleration begins. It happens in stages, like runners passing a baton in a relay race. The protons enter a small linear accelerator and gain their first burst of speed. Then they transfer to a circular ring called the booster, then to the proton synchrotron, then to the superproton synchrotron, each ring larger and faster than the last. By the time they enter the main LHC ring, they're already traveling at 99.9% of light speed. But that's not fast enough. The LHC accelerates them further. Powerful radio frequency cavities apply electric fields at precisely timed intervals, kicking the protons to higher and higher energies. With each lap, they gain speed, and as they approach the ultimate cosmic speed limit, something strange happens. Time slows down for them. This isn't speculation. It's confirmed physics, tested millions of times. At these speeds, Einstein's theory of special relativity takes over. From the proton's perspective, traveling at 99.9999% of light speed, the entire 17-mile journey around the ring is compressed. Time dilates. What takes microseconds in our reference frame happens in a fraction of that time. From the proton's viewpoint, the protons also gain mass. A proton at rest weighs almost nothing, about 1.67 times 10 to the minus 27 kilograms. But a proton moving at near light speed becomes 7,000 times heavier, not because new matter appears, but because kinetic energy has mass, and at these speeds, the energy is enormous. This is the reality of relativity, playing out 11,000 times per second beneath the French and Swiss countryside. And then, when the moment is right, the beams cross, not gently, not slowly. The protons collide at a combined energy of 13 trillion electron volts. The collision point is smaller than an atom, for an instant briefer than thought. The temperature spikes to several trillion degrees hotter than the core of any star, hotter than anything in the observable universe today. In that heat, matter doesn't just break apart. It transforms. Energy becomes mass. Particles that haven't existed since the Big Bang suddenly flash into existence for a fraction of a second before decaying into cascades of other particles. And surrounding those collision points are the detectors, machines the size of cathedrals, weighing thousands of tons, packed with sensors capable of tracking particles that exist for less than a trillionth of a second. This is what CERN does, hour after hour, day after day. It rewinds the clock. It takes us back to the first moments of creation, and from those moments, we learn what the universe is truly made of. Let's follow a single proton on its journey. Not metaphorically, actually trace its path from the moment it enters the system to the instant it collides with another proton and ceases to exist as a distinct entity. It begins in a small red bottle, no bigger than a fire extinguisher. Inside that bottle is hydrogen gas, simple, ordinary hydrogen, the most abundant element in the universe. Each hydrogen atom consists of one proton and one electron orbiting around it. For now, they're stable, neutral, unremarkable. The hydrogen is released into a device called a duoplasmatron. This machine uses electric fields to strip the electrons away, leaving only the proton's bare nuclei, positively charged, ready to be accelerated. Imagine billions of these protons, now ionized, forming a cloud of positive charge. The first acceleration stage is a linear accelerator called LINAC-4. It's 50 meters long, and its job is straightforward. Give the protons their first significant push. By the time they exit LINAC-4, they're traveling at about 32% the speed of light. That sounds fast, and it is, but it's only the beginning. From LINAC-4, the protons transfer to the proton synchrotron booster, a circular ring about 50 meters in diameter. Here, they're accelerated further. The ring uses synchronized magnetic fields to keep the protons on a curved path, while radio frequency cavities boost their energy with each lap. By the time they leave the booster, they're moving at 91.6% of light speed. Next comes the proton synchrotron, or PS, a ring 628 meters around. Built in 1959, the PS is one of the oldest machines still operating at CERN, and it remains an essential part of the acceleration chain. Here, the protons gain even more energy. reaching 99.93% of light speed. Then they move to the superproton synchrotron. The SPS, a ring nearly 7 kilometers in circumference. This is the final stage before entering the LHC itself. By the time protons exit the SPS, they're traveling at 99.9998% of light speed. And yet, they still aren't fast enough. When the protons finally enter the Large Hadron Collider's main ring, they've already been accelerated through for separate machines, each one pushing them closer to the ultimate cosmic speed limit. But the LHC is designed to take them right to the edge, 16 radio frequency cavities, each one operating at 400 MHz, deliver precisely timed kicks of energy. With each pass through these cavities, the protons gain a little more speed, a little more energy. After thousands of laps, they reach their final velocity, 99.9999991% the speed of light. At this speed, the difference between the protons and light itself is almost immeasurable. If a photon and a proton both traveled the 17-mile ring, the photon would complete the circuit only microscopically faster. Let's talk about what that speed actually means. A proton in the LHC completes one full lap, or 17 miles, in just 89 microseconds. That's 89 millionths of a second. In a single second, that proton circles the ring 11,245 times. If you were somehow able to watch it, you wouldn't see motion. You'd see a blur, a quantum probability smear occupying all points on the ring simultaneously. But something else happens at these speeds. Something predicted by Einstein over a century ago, and confirmed in every high-energy experiment ever conducted. Time dilates. From our perspective, standing still relative to the LHC, a second is a second. But from the proton's perspective, traveling at 99.9999991% of light speed, time passes about 7,000 times more slowly. What feels like a second to us is experienced as a tiny fraction of that time by the proton. It ages slower. Its internal processes, if we could meaningfully speak of such things for a fundamental particle, occur in a stretched, slow temporal frame. This isn't theoretical. It's measured. Particles that decay quickly when at rest live far longer when accelerated to near light speed. Their decay lifetimes extend proportionally to their velocity, exactly as relativity predicts. The protons themselves don't decay, they're stable, but the principle is the same. The protons also gain mass, or more precisely, their relativistic mass increases. A stationary proton has a rest mass of approximately 938 million electron volts, divided by the speed of light squared. But a proton in the LHC, moving at extreme velocity, has an energy of 6.5 trillion electron volts. That energy contributes to its effective mass. If you could somehow weigh it, it would be nearly 7,000 times heavier than a stationary proton. All of this energy, kinetic energy, mass energy, the immense electromagnetic fields needed to keep the beam focused, must be managed with extraordinary precision. The slightest misalignment, the tiniest fluctuation in magnetic field strength, and the beam would drift off course. Protons would strike the tunnel walls, releasing their energy in a catastrophic shower of secondary particles. That's why the LHC has a beam dump system. If sensors detect anything wrong, a magnet warming up, a vacuum failure, an unstable orbit, the beam is extracted in less than a millisecond. Kicking magnets divert the protons out of the ring and into massive graphite absorbers, blocks of material designed to safely dissipate the energy. The beam carries as much kinetic energy as a speeding freight train. Releasing that energy in an uncontrolled way could damage the machine irreparably. But when everything works, when all systems are green and the beams are stable, the moment arrives. The two beams, one traveling clockwise, the other counterclockwise, are brought into focus. Powerful quadrupole magnets squeeze the beams until they're narrower than a human hair. At 4 points around the ring, the beams cross. The protons pass through each other in bunches, billions at a time. Most protons miss. Space, even at the subatomic scale, is mostly empty. A proton is incredibly tiny, about 1 femtometer across, which is 10 to the minus 15 meters. Even when billions of protons pass through each other, the vast majority sail through unscathed. But some collide, when two protons moving in opposite directions, each carrying 6.5 trillion electron volts of energy, meet head-on. The combined energy is 13 trillion electron volts. That's 13 tera-electron volts, or 13 TeV, concentrated in a region smaller than the nucleus of an atom. The temperature in that infinitesimal point spikes to several trillion degrees Kelvin. To put that in perspective, the core of our sun burns at about 15 million degrees. The center of a massive star might reach a few billion degrees during supernova. The collision point inside the LHC exceeds all of that by orders of magnitude. At such temperatures, protons don't just break apart, they dissolve. The quarks and gluons that normally bind together to form protons are liberated. If only for an instant, energy transforms directly into matter, following Einstein's famous equation E equals mc squared. Particles that haven't existed freely since the universe was a fraction of a second old suddenly appear. Higgs bosons, top quarks, W and Z bosons, exotic hadrons containing strange charm and beauty quarks, occasionally even rarer phenomena pairs of Higgs bosons, or particles theorists have only dreamed of. The collision produces not one or two particles but hundreds. They spray outward in all directions at speeds approaching light speed themselves. And in that expanding shower of debris, encoded in the energies and trajectories and identities of each particle, is information. Information about the laws of physics. Information about the forces that govern the universe. Information about why anything exists at all. That's what the detectors are for. They catch the debris, and from that debris, physicists reconstruct what happened in the collision, working backward from effect to cause. From observation to understanding. This is the journey of a proton. From a bottle of gas to the fastest speeds achievable by matter. From ordinary hydrogen to a fragment of the early universe. From existence as a stable particle to transformation into energy and then into new forms of matter. And this journey happens billions of times per second, day after day, year after year, in the circular cathedral buried beneath the border of Switzerland and France. For 50 years, physicists had a problem they couldn't solve. Their equations worked beautifully. They predicted how particles behaved, how forces interacted, how the universe held itself together. But there was a hole in the mathematics, an absence that made no sense. According to the standard model, the framework describing all known particles and forces, particles should have no mass, zero, nothing. Every electron, every quark, every fundamental piece of matter should weigh exactly nothing and fly through the universe at the speed of light forever. Obviously, this is wrong. You have mass. The chair beneath you has mass. The Earth, the Sun, the galaxies all have mass. Something was missing from the equations. Something fundamental wasn't understood. In 1964, several physicists, working independently, proposed an answer. There must be a field, they said, an invisible field that fills all of space, permeating every point in the universe. When particles move through this field, they interact with it. That interaction creates drag, resistance. And that drag is what we experience as mass. Think of it like this. Imagine walking through air. You move freely, encountering only minimal resistance. Now imagine walking through water. The resistance increases. You feel drag. You slow down. The water doesn't stop you, but it impedes your motion, making movement require more effort. The field these physicists proposed works similarly, except it doesn't slow particles down. Instead, it gives them inertia, the property we call mass. Particles that interact strongly with the field are heavy. Particles that interact weakly are light. Particles that don't interact at all, like photons, remain massless and travel at light speed forever. This field needed a name. It was eventually called the Higgs field, named after one of the physicists who proposed it, Peter Higgs, a soft-spoken theoretical physicist working at the University of Edinburgh. But if the field exists, quantum mechanics demands something else must exist too, a particle. Every field in quantum theory is associated with a quantum, a discrete unit, a particle that represents an excitation of that field. Photons are the quanta of the electromagnetic field. Gluons are the quanta of the strong force field. If the Higgs field is real, there must be a Higgs boson particle that embodies the field itself. Finding it, however, would be nearly impossible. The Higgs boson is unstable. It exists for less than a trillionth of a second before decaying into other particles. You can't catch it, you can't bottle it, you can't observe it directly. The only way to know it existed is to see the particles it decays into and work backward, reconstructing its brief existence from the debris it leaves behind. For decades, physicists searched. They built larger and larger colliders. They smashed particles together at higher and higher energies, hoping to produce a Higgs boson and catch its signature. Experiments at CERN's Large Electron Positron Collider came close, seeing hints but never definitive proof. Experiments at Fermilab in the United States saw tantalizing suggestions, but nothing conclusive. Some physicists began to doubt. Maybe the Higgs boson didn't exist. Maybe the theory was wrong. Maybe mass came from something entirely different, a mechanism no one had thought of yet. Then came the Large Hadron Collider. The LHC was designed, in part, to find the Higgs. Its collision energy was high enough that, if the Higgs boson existed anywhere within the theoretically allowed mass range, it should appear. If the LHC didn't find it, that would be nearly as significant as finding it proof that the entire theoretical framework needed rethinking. The machine turned on in 2008. The accident in September of that year delayed operations, but by 2010, beams were colliding regularly. Data began to accumulate. Billions of collisions, trillions of particles, countless measurements. Physicists knew what they were looking for. The Higgs boson, if it existed, would decay in predictable ways, sometimes into pairs of photons, sometimes into pairs of Z-bosons, sometimes into pairs of bottom quarks. Each decay channel had its own signature, its own combination of particles and energies that could be distinguished from background noise. But distinguishing signal from noise is extraordinarily difficult. Most collisions produce ordinary particles through well-understood processes. The Higgs signal, if present, would be buried under a mountain of background events. Finding it required analyzing billions of collisions, applying sophisticated statistical techniques, and searching for a tiny excess of small bump in the data, where theory predicted the Higgs should appear. The searches were conducted by two independent collaborations. Atlas and CMS each used different detectors, different analysis methods, different teams of physicists. This redundancy was deliberate. If both found the same signal, it was almost certainly real. If only one did, skepticism would remain. By late 2011, hints were emerging. Both Atlas and CMS saw small excesses. Around 125 billion electron volts, 125 GeV in the units physicists use. The signal wasn't strong enough to claim discovery yet, but it was intriguing. The teams kept analyzing, adding more data, refining their methods. Then came July 4, 2012. At CERN, in an auditorium packed with physicists, journalists and curious observers, the results were announced. ATLAS presented first. They had found a new particle. The excess was clear, far beyond what random fluctuations could explain. The statistical significance was 5 sigma, the gold standard in particle physics, meaning the probability that the signal was just noise was less than 1 in 3. And 500,000. CMS presented next. They had found the same thing. A particle at 125 GeV, seen in multiple decay channels, with 5 sigma significance. The room erupted in applause. Some people cried. Decades of work, decades of hoping and searching and doubting had culminated in this moment. Peter Higgs sat in the audience. He was 83 years old. He had proposed the field and the particle 48 years earlier, in 1964, when particle physics was still in its infancy. For nearly half a century, he had wondered whether his mathematics actually described reality, or whether it was just an elegant idea that nature chose not to implement. Now he knew. Tears ran down his face as the results were shown. The field was real. The particle was real. His name would forever be attached to one of the most important discoveries in the history of science, but the discovery raised new questions almost immediately. The Higgs boson has a mass of 125 GeV. That number is not arbitrary. It determines the strength of the Higgs field, the way it interacts with other particles, and critically the stability of the universe itself. With a mass of 125 GeV, combined with the measured mass of the top quark, calculations suggest that the vacuum of space, the lowest energy state of the Higgs field, might not be the absolute lowest possible state. There might be a deeper minimum, a truer vacuum with lower energy. If that's the case, our universe is in a state called metastability. What does that mean? Imagine a ball sitting in a shallow valley on the side of a hill. The ball is stable for now. Small disturbances might roll it around a bit, but it settles back. However, if a large enough disturbance came along a quantum fluctuation, perhaps the ball could tunnel through the valley wall and roll down to a deeper valley. On the other side, that deeper valley represents the true vacuum. If that happens, a bubble of true vacuum would form. Inside the bubble, the Higgs field would have a different value. Particle masses would change. The forces that hold atoms together would weaken or strengthen. Chemistry would fail. Stars wouldn't burn. Life couldn't exist. The bubble would expand at the speed of light, consuming everything it touched. You would never see it coming. One moment, reality as we know it would exist. The next, it would be gone, replaced by a universe with different laws. This is called vacuum decay. It's theoretically possible, but the time scale is uncertain. Calculations suggest that if our universe is metastable, the time for such a decay to occur could be far longer than the current age of the universe, trillions upon trillions of years. We might be safe for an incomprehensibly long time, or we might not be. The Higgs boson's self-coupling, the way Higgs bosons interact with other Higgs bosons, is key to understanding this. If physicists can measure that self-coupling precisely, they'll know whether the vacuum is truly unstable or whether we're safe in a deeper valley than current calculations suggest. Right now, the measurements aren't precise enough. The Higgs self-coupling has been constrained but not definitively measured. Finding it requires observing events where two Higgs bosons are produced in the same collision, something that's roughly 1,000 times rarer than producing a single Higgs. The LHC is searching. Every year, more data accumulates. Every year, the sensitivity improves. Eventually, the answer will be known. But regardless of the vacuum stability question, the discovery of the Higgs boson was monumental. It confirmed a prediction made half a century earlier. It completed the Standard Model, filling in the last missing piece. It earned Peter Higgs and Francois Inlet the 2013 Nobel Prize in Physics. And it proved that even the most abstract mathematics, even the most speculative ideas about invisible fields permeating space, can turn out to be true. The universe doesn't care about our intuitions. It operates according to principles that are often strange, counterintuitive, and surprising. The Higgs field is one of those principles, and the Higgs boson, that tiny, fleeting particle that exists for less than a trillionth of a second, is the proof that humanity can uncover even the deepest secrets nature hides. The search for the Higgs took 50 years. Understanding what it means might take 50 more. Every fundamental particle interacts with other particles. Electrons repel other electrons through electromagnetism. Quarks bind to other quarks through the strong force. Photons carry forces between charged particles. These interactions follow rules that physicists have tested millions of times. But the Higgs boson is different. According to the Standard Model, the Higgs can do something no other fundamental particle can do in quite the same way. It can interact with copies of itself. This is called Higgs self-coupling, and it might determine the fate of the universe. Imagine 3 Higgs bosons appearing at a single point in space, meeting for an instant before decaying, or for Higgs bosons connecting in a single event. These interactions are written into the mathematics of the Standard Model. They must happen. The question is whether what the math predicts actually matches what nature does. Finding one Higgs boson took decades and billions of collisions. Finding two Higgs bosons produced in the same event, the signature of self-coupling is about 1,000 times harder. The probability is extraordinarily low. Even with the massive amounts of data the LHC collects, such events are exceedingly rare. But scientists are searching. The reason this matters goes far beyond particle physics. The Higgs self-coupling determines the shape of the Higgs potential, the mathematical function that describes how the Higgs field behaves at different field values. Think of this potential as a landscape. The Higgs field sits in a valley. The shape of that valley controls how stable the universe is. If the valley is deep and smooth, the universe is stable. The field rests at the bottom and will stay there forever. Small fluctuations might disturb it, but it always returns to equilibrium. But if the valley has thin walls and there's a deeper pit somewhere else, a lower energy state, then the universe is metastable. The field could, through quantum tunneling, jump from our valley to the deeper one. And if that happens, everything changes. This is where vacuum decay comes in. Quantum mechanics allows particles and fields to do things that classical physics forbids. A ball sitting in a valley can't spontaneously jump over a hill, but in quantum mechanics it can tunnel through. The probability is usually low, but it's not zero. If the Higgs field tunnels to a lower energy state, a bubble of true vacuum forms. Inside the bubble, the Higgs field has a different value. Since the Higgs field gives particles their mass, changing its value changes particle masses. Electrons might become heavier. Quarks might become lighter. The electromagnetic force might strengthen. The strong nuclear force might weaken. Atoms would no longer hold together. Chemistry would fail. Stars would collapse or explode. Galaxies would disintegrate. The bubble expands at the speed of light. Nothing can escape it. There's no warning. One moment, you're living in a stable universe. The next moment, the laws of physics change, and everything ceases to exist as it was. This sounds terrifying. But before you panic, understand a few things. First, this is theoretical. There's no confirmed evidence that vacuum decay will happen. The calculations are based on the measured masses of the Higgs boson and the top quark, and they suggest metastability is possible. But uncertainties remain. Small changes in the measurements or corrections from physics beyond the standard model could shift the conclusion. Second, even if the universe is metastable, the timescale for decay could be unimaginably long. Some estimates suggest the lifetime could be 10 to the 100 years, or more, far longer than the current age of the universe, which is less than 10 to the 10 years. If that's true, we're safe for trillions upon trillions of years. Third, vacuum decay might not be triggered randomly. It might require specific conditions, extreme energy densities, black hole evaporation, cosmic events we don't fully understand. Those conditions might never occur in our observable universe. Still, the possibility is unsettling, and the only way to know for sure is to measure the Higgs self-coupling precisely. Right now, experiments at the LHC have constrained the value. They know it lies somewhere between negative 0.7 and positive 6 times the standard model prediction. That's a wide range. Narrowing it requires finding events where the Higgs bosons are produced simultaneously. This is extraordinarily difficult. The production rate for double Higgs events is tiny, only about 1 event per trillion collisions, compared to 1 per 10 billion for single Higgs production. And even when such an event occurs, it must be distinguished from background processes that look similar. The high luminosity upgrade to the LHC, scheduled to begin in 2029, will help by increasing the collision rate by a factor of 5 to 7. It will produce many more double Higgs events. Advanced analysis techniques using machine learning will improve the ability to identify these rare events. The future circular collider, if built, would do even better. Its higher energy and luminosity would allow precise measurement of the Higgs self-coupling, potentially resolving the vacuum stability question once and for all. If the measurement matches the standard model prediction exactly, it would confirm that the universe is likely metastable, balanced on a knife's edge, but stable for an incomprehensible length of time. If the measurement deviates from the prediction, it would indicate new physics. Perhaps additional Higgs-like particles exist, Perhaps supersymmetry stabilizes the vacuum. Perhaps the universe is actually fully stable and our calculations missed something. Either answer changes our understanding of reality. Consider what it would mean if the universe truly is metastable. It would imply that the current state of existence, the laws of physics, the constants of nature, the delicate balance that allows stars to burn and atoms to form is temporary. It's not the final state, it's just a long-lived intermediate stage. On the other hand, if new physics stabilizes the vacuum, it would mean we're missing something fundamental. The standard model would be incomplete in ways we haven't yet imagined. New particles, new forces, new principles would need to be discovered. The Higgs boson, discovered in 2012, opened a door. Behind that door are more questions. How does the Higgs interact with itself? Is the vacuum stable? What happens at higher energies? Are there more Higgs-like particles? Every measurement brings us closer to answers. Every collision at the LHC is another chance to observe the rare events that reveal the truth. The physicists analyzing the data aren't just checking boxes on a list of predictions. They're probing the fundamental structure of reality, asking whether the universe we inhabit is in its final form or just passing through. And perhaps most remarkably, they're doing this by smashing protons together and watching what happens a process. That seems almost crude, but is, in fact, one of the most sophisticated and precise scientific endeavors humanity has ever undertaken. The universe may be balanced on a knife's edge, or it may be rock-solid stable. The answer is hidden in the interactions of particles so fleeting they barely exist. And we're learning to read those interactions one collision at a time. Between galaxies where no stars burn and no planets spin, the temperature drops to about negative 150 degrees Fahrenheit. This is the natural cold of the void. The background radiation left over from the Big Bang keeps space from reaching absolute zero, but just barely. The Large Hadron Collider operates colder than that. Specifically, the superconducting magnets that bend the particle beams require temperatures of minus 456 degrees Fahrenheit, nearly 2 degrees colder than intergalactic space. It's one of the coldest places in the known universe. Why such extreme cold? The answer lies in the physics of superconductivity. Certain materials, when cooled below a critical temperature, lose all electrical resistance. Current flows through them without generating heat, without losing energy. This allows the LHC's magnets to carry enormous currents up to 12,000 amperes and generate magnetic fields powerful enough to bend protons traveling at 99.9999% of light speed. A conventional magnet would melt under such conditions. A superconducting magnet simply bends space around itself, guiding particles along their circular path with no energy lost to heat. But achieving superconductivity requires cooling the magnets to just 1.9 degrees above absolute zero. That's 9 Kelvin or minus 271 degrees Celsius. This is accomplished using liquid helium. Helium is unique, it's the only substance that remains liquid at temperatures this close to absolute zero. Everything else freezes solid. 96 tons of helium circulate through the LHC's cooling system, flowing through pipes and channels that wrap around each magnet. The system is a marvel of cryogenic engineering. The helium is first cooled to 4.5 Kelvin using conventional refrigerators. Then it's further cooled by reducing the pressure, allowing it to evaporate and carry away heat, a process called evaporative cooling. This brings the temperature down to 1.9 Kelvin. Maintaining this cold is a continuous battle. Heat leaks in from the environment. The Earth itself, with a temperature of around 10 degrees Celsius at the tunnel depth, is warm compared to the magnets. Insulation helps, but it's not perfect. The cooling system must constantly remove heat to keep the magnets superconducting. If the temperature rises even a single degree, disaster strikes. The magnets lose superconductivity. Electrical resistance suddenly appears. The current generates heat. More heat causes more warming. The feedback loop is called a quench, and it happens fast. In 2008, during the LHC's initial startup, exactly this occurred. A faulty electrical connection created a spark. The spark heated a small section of the machine. The heating caused helium to vaporize explosively. Helium expands by a factor of 700. When it goes from liquid to gas, the pressure wave ripped vacuum pipes from their mountings and damaged over 50 magnets. The repair took 14 months. Engineers had to warm the entire machine to room temperature, replace the damaged components, and then cool it back down, a process that alone takes weeks. The cost ran into tens of millions of dollars. Lessons were learned. Additional safety systems were installed. Better monitoring was implemented. Electrical connections were reinforced. And since then, the LHC has operated with remarkable reliability, but the fragility remains. A bird dropping a piece of bread on an outdoor power unit once caused a shutdown. A weasel chewing through electrical cables knocked the system offline. These incidents sound almost comical, but they illustrate the precision required. When you're operating at the edge of physical extremes, even the tiniest disruption has consequences. When the cold holds, though, something beautiful happens. The superconducting magnets generate magnetic fields of 8.3 Tesla, more than 150,000 times stronger than Earth's magnetic field. These fields curve the paths of protons with exquisite precision. Each magnet is aligned to within fractions of a millimeter. The magnetic field strength is controlled to within parts per million. The beam orbits are adjusted dynamically, thousands of times per second, to keep the protons on track. And all of this happens at temperatures colder than the vast majority of the universe. It's a strange juxtaposition. The coldest place humans have ever created exists alongside the hottest temperatures, inside the collision points where protons smash together at trillions of degrees. Cold and hot, separated by meters, both extremes necessary for the machine to function. The cryogenic system also has to deal with another challenge: radiation. As particles collide, they produce secondary particles, some of which escape the detectors and strike the magnets. This radiation deposits energy, warming the magnets ever so slightly. The cooling system must remove this heat continuously. There's also the sheer scale. 17 miles of tunnel, over 1,000 magnets, thousands of tons of superconducting cable. All must be kept at 1.9 Kelvin. It's the largest cryogenic system ever built, dwarfing anything else in existence. The helium itself is a precious resource. While helium is the second most abundant element in the universe, it's rare on Earth. Most of our helium comes from natural gas deposits, where it accumulates over millions of years from radioactive decay of uranium and thorium deep underground. Once released into the atmosphere, helium escapes into space. It's so light that Earth's gravity can't hold it. CERN recycles almost all the helium used in the LHC. A sophisticated recovery system captures evaporated helium, compresses it back into liquid form, and returns it to the cooling loop. Less than 1% is lost each year. This recycling is essential. Without it, the operating costs would be astronomical and the environmental impact significant. Helium is used not just at CERN, but in MRI machines, in scientific research, and in industrial applications worldwide. Conservation matters. So beneath the fields of France and Switzerland, inside a tunnel drilled through rock, surrounded by insulation and vacuum chambers and cooling pipes, the magnets rest at 1.9 Kelvin, colder than the cosmic microwave background, colder than the voids between galaxy clusters, among the coldest places in the observable universe, and they hold that cold steadily and reliably, day after day, enabling protons to race in circles at nearly the speed of light, colliding trillions of times, revealing the secrets hidden in the structure of matter itself. In September 2023, physicists at CERN's Alpha experiment answered a question that had lingered for decades. With elegant simplicity, antimatter falls down, just like everything else. The result might seem obvious. Of course, gravity pulls on everything the same way. But nothing in science can be assumed without measurement. For years, the Alpha collaboration had been working to trap antihydrogen atoms, the antimatter mirror of the simplest element. Each atom consisted of an antiproton orbited by a positron, held suspended in a magnetic bottle more than 1,000,000 times deeper. than Earth's gravitational pull, the challenge was exquisite. To see gravity's effect, the team had to turn off those powerful magnetic fields and watch what happened as the anti-hydrogen atoms drifted free. In the ALPHAG apparatus, a vertical tube allowed the anti-atoms to move upward or downward. Detectors at each end recorded where they arrived. The measurement required counting individual atoms one by one. As they fell, or if some radical new physics were at work rose upward, certain atoms fell down. The measurement showed a antimatter accelerating toward Earth at 9.8 meters per second squared, within experimental uncertainty. No anti-gravity, no repulsion, just the same gentle pull that governs everything from apples to galaxies. Why did the question matter so much? Because Einstein's general relativity predicts that all forms of mass energy should respond identically to gravity, a principle called the equivalence principle. While indirect evidence had always supported this, no one had actually watched free antimatter fall before. The alpha result represented the first direct observation, closing a conceptual gap that had existed since antimatter's discovery. Yet this validation deepens another mystery. The universe began with equal amounts of matter and antimatter. They should have annihilated completely, leaving only light. Instead, a tiny surplus of matter survived, about one extra particle for every billion matter-antimatter pairs. We are the descendants of that surplus, the remnant that refused to vanish. The antimatter asymmetry grows more puzzling each time we confirm that matter and antimatter follow the same rules. If they're truly symmetric, why does only one kind remain? Deep beneath the prairie at Fermilab, muons race around a ring while physicists watch them wobble. The wobble, technically the anomalous magnetic moment, had become one of the most tantalizing puzzles. In particle physics, Fermilab muon G2 experiment measures how muons spin in a magnetic field. According to quantum mechanics, a muon's magnetic moment should be almost exactly twice its spin angular momentum, hence G2, where G is the ratio that should equal 2, but almost exactly leaves room for quantum fluctuations. Virtual particles constantly pop in and out of existence around the muon, tugging at its spin like invisible hands. The standard model can calculate these effects with extraordinary precision. In 2001, the experiment at Brookhaven National Laboratory found something unexpected. The measured wobble exceeded the standard model prediction, not by much, a discrepancy of about 0.1%, but enough to reach 3.7 standard deviations. In physics, 5 sigma means discovery, 3 sigma means intrigue. Fermilab rebuilt the experiment, transporting Brookhaven's superconducting storage ring on a remarkable journey through Long Island suburbs and down the Mississippi River to Illinois. By 2023, the new measurements confirmed the Brookhaven anomaly with greater precision. The discrepancy had reached 5.0 sigma. Then in June 2025, the final measurement achieved unprecedented precision of 127 parts per billion, surpassing the initial goal. But theoretical physics caught up. New calculations using lattice quantum chromodynamics supercomputers, solving the equations of the strong force on a discrete space-time grid, revised the standard model prediction upward. The gap narrowed. Some calculations now bring theory and experiment into closer agreement, though debates about the correct theoretical value continue. The muon's wobble had seemed to point toward new particles, unseen forces, extensions to the standard model. Those hints haven't disappeared entirely, but they've grown more subtle. The story illustrates how progress in physics requires both experimental precision and theoretical refinement, each sharpening the other until certainty emerges or genuine new physics reveals itself. In April 2022, the CDF collaboration at Fermilab announced a measurement that sent ripples through the physics community. After analyzing data from the now-defunct Tevatron Collider, they reported the mass of the W boson, a fundamental carrier of the weak force, at 80,433 MeV. This exceeded the standard model prediction by 76 MeV, a 7 sigma deviation. Scientific American 7 sigma. In particle physics, that number demands attention. 5 sigma means discovery. 7 sigma suggests either revolutionary new physics or a subtle experimental error. The W boson's mass connects intimately to the Higgs field, electroweak symmetry breaking, and the masses of other fundamental particles. An anomaly here could unravel decades of theoretical understanding, or point towards something extraordinary. The physics community responded with a mixture of excitement and caution. Some theorists began constructing models to explain the heavy W, perhaps additional Higgs bosons, new gauge bosons, or exotic fermions coupling to the electroweak sector. Others scrutinized the CDF analysis, examining every assumption and systematic uncertainty. Then CERN responded. In September 2024, the CMS experiment at the LHC announced their own W boson mass measurement, 360 MeV, perfectly consistent with the standard model and contradicting the CDF result. The Atlas collaboration's earlier measurement also agreed with theory. Where CDF saw a 7 sigma anomaly, the LHC experiments saw confirmation of predictions. Naturally, discrepancy remains unresolved. 3 major experiments, Atlas, CMS, and CDF, used different collision environments, different detectors, different analysis techniques. CDF analyzed proton-antiproton collisions at lower energy with 10-year-old data. Atlas and CMS study proton-proton collisions at higher energy with modern detectors. Which is correct? The standard model survives for now. But the CDF result hasn't been explained away. It stands as a reminder that experimental physics is hard, that different approaches can yield different answers, and that even 7 sigma deviations can coexist with contradictory evidence. The crisis has become a puzzle waiting for resolution. For decades, physicists believed hadrons came into varieties, baryons made of 3 quarks, and mesons made of a quark-antiquark pair. This simple picture emerged from the quark model that Murray Gell-Mann and George Zweig developed in the 1960s. The strong force, mediated by gluons, binds quarks into these familiar configurations. But the rules permitted more exotic possibilities. If 3 quarks combine together, why not 4? Why not 5? The quantum chromodynamics equations don't forbid such states, but confirming their existence required finding them in nature. CERN's LHCb experiment specializes in studying beauty quarks, the second heaviest quark flavor, in collisions that produce beauty quarks and their anti-quarks. Exotic combinations sometimes emerge from the chaos. In July 2022, LHCb announced the discovery of 3 new exotic hadrons in a single analysis, a pentaquark and 2 tetraquarks, all containing charm quarks. These discoveries expanded an emerging bestiary. By 2024, physicists had confirmed 5 pentaquarks and 18 tetraquarks. Most contain at least 1 charm quark, which makes them more stable and easier to detect. The pentaquarks consist of 4 quarks and 1 anti-quark, while tetraquarks contain 2 quarks and 2 anti-quarks. CERN Korea, would do these exotic states teach us? They reveal new facets of the strong force. Quarks bind through the exchange of gluons, and gluons themselves carry color charge. This allows gluons to interact with each other, creating complex dynamics impossible in electromagnetism. The exotic hadrons might be tightly bound objects, with all quarks occupying a compact volume, or they might be loosely bound molecules of conventional hadrons, a meson, and a baryon orbiting each other like atoms in a molecule. Distinguishing these structures requires precise measurements of masses, decay patterns, and quantum numbers. The strong force operates at distance scales of about 1 femtometer, a millionth of a billionth of a meter, where quarks and gluons exhibit behaviors that still surprise us. Each new exotic hadron adds a data point, constraining theories, revealing patterns. The bestiary grows, and with it, our understanding of how matter holds together at its most fundamental level. In March 2024, the CMS experiment announced something remarkable. They had observed quantum entanglement between top quarks and their antimatter partners, created in the highest energy collisions ever studied. CMSD quarks live for only about K-25 seconds before decaying to brief, even for them to bind into hadrons. This ephemeral existence makes them unique windows into quantum mechanics, because they decay before the strong force can dress them in clouds of virtual gluons. and quark-antiquark pairs, when the LHC creates a top quark and top antiquark pair. Quantum mechanics predicts they should be entangled. Einstein called it spooky action at a distance, though it's neither spooky nor action and doesn't violate relativity. Entanglement means the particles share a quantum state. Measuring one instantly determines properties of the other, no matter how far apart they travel. But observing this entanglement in top quarks posed extraordinary challenges. The particles decay almost immediately, each producing a cascade of daughter particles, W bosons. Bottom quarks, jets of hadrons. The detector records hundreds of particles from each collision. Buried in that complexity lies information about the original top quark spins. The CMS team developed analysis techniques sensitive to correlations in the decay product's angular distributions. If the top quarks were entangled, certain decay patterns would occur more frequently than if they were independent. The signal emerged clearly, entanglement at 5.1 sigma significance. Atlas confirmed it at 5.7 sigma. Naturethis represents the highest energy observation of quantum entanglement ever made. Particles with masses 175 times heavier than protons, existing in entangled states for less than a trillionth of a second. Quantum mechanics, formulated in the 1920s to describe atoms and electrons, holds even in these extreme conditions. The observation also opens new possibilities. If quantum mechanics were subtly modified at high energies, perhaps by quantum gravity effects, top quark entanglement might deviate from predictions. So far, the measurements agree perfectly with theory. But as precision improves, these entangled titans might yet reveal surprises lurking at the intersection of quantum mechanics and relativity. We exist because of a cosmic accident, or perhaps not an accident, perhaps a subtle asymmetry built into nature's laws, one that physicists have been trying to understand for decades. In the first microsecond after the Big Bang, the universe was hot enough that particles and antiparticles were continuously created and destroyed. For every electron that appeared, a positron materialized. For every quark, an antiquark. Matter and antimatter emerged in nearly perfect balance. Somewhere in those first moments, one extra matter particle appeared for every billion particle-antiparticle pairs. As the universe cooled, the vast majority of matter and antimatter annihilated into photons. Only that tiny surplus of matter survived. Everything we see, galaxies, stars, planets, people, descends from that 1 in a billion excess. To create such an asymmetry requires 3 conditions, outlined by Andrei Sakharov in 1967. First, processes that violate baryon number conservation. Second, violation of C-symmetry charge and CP symmetry combined charge and parity. Third, departure from thermal equilibrium as the universe expanded. The Standard Model contains CP violation. In 1964, James Cronin and Val Fitch discovered it in kaon decays. The phenomenon arises from a complex phase in the CKM matrix, which describes how quarks mix under the weak force. LHCb has spent years studying CP violation in beauty mesons, charmed mesons, and in 2025 finally observed it in beauty baryons. CERNiac new measurement of CP violation adds precision. The LHCb collaboration found that beauty lambda baryons decay differently than their antiparticles, at a level of 0.8%. The observation, reported in July 2025, marked the first time CP violation had been confirmed in baryons particles made of 3 quarks, like protons and neutrons. But here's the problem: the CP violation in the Standard Model is far too small. The 1 in a billion asymmetry requires stronger effects than the CKM matrix provides. Calculations suggest we need new sources of CP violation beyond what the Standard Model describes, perhaps in the neutrino sector, perhaps in some undiscovered interaction at higher energies. The matter-antimatter asymmetry proves that new physics must exist. We live because the universe is not perfectly symmetric. The challenge is finding where that asymmetry hides, what generates it, why it takes the specific value that allowed matter to survive. Every LHCb measurement narrows the possibilities. But the ultimate answer remains elusive, a mystery written in the very fact of our existence. Ordinary matter, everything made of atoms. Everything we can see comprises roughly 5% of the universe's total mass energy. Another 27% is dark matter, detectable only through its gravitational effects. The remaining 68% is dark energy, something even more mysterious. Dark matter doesn't emit, absorb, or scatter light. It doesn't interact through the electromagnetic or strong nuclear forces. Yet its presence is undeniable. Galaxies rotate too fast for their visible matter to hold them together. They would fly apart without additional gravitational pull. Galaxy clusters contain far more mass than their luminous stars and gas can account for. The cosmic microwave background carries subtle imprints of dark matter's influence. In the early universe, for decades, the leading candidate was WIMPs weakly interacting massive particles. The idea was elegant. If dark matter particles have masses around the electroweak scale, tens to hundreds of GeV, and interact via the weak force, their relic abundance from the Big Bang naturally matches observations. The LHC should produce WIMPs in collisions. Underground detectors should observe them scattering off atomic nuclei. ARXIV searches came up empty. ATLAS and CMS have looked for signs of WIMPs in missing energy particles that escape undetected, carrying momentum away. They've searched for new massive particles that could serve as dark matter. No definitive signals have emerged. Direct detection experiments deep underground have grown exquisitely sensitive, capable of detecting a single collision of a dark matter particle with a xenon atom. They found nothing above background expectations. WIMPs haven't been ruled out entirely, but the parameter space has narrowed dramatically. Physicists have turned to alternatives. Axions are hypothetical particles proposed to solve the strong CP problem. More on that later. If they exist with the right mass, around a microelectronvolt, they could constitute dark matter. Multiple experiments are searching for axions by attempting to convert them into photons. Using strong magnetic fields, sterile neutrinos represent another possibility. Unlike the three known neutrino flavors, sterile neutrinos wouldn't interact via the weak force at all, only through gravity, and possibly through mixing with ordinary neutrinos. With masses in the cave range, they could comprise dark matter while explaining various astrophysical anomalies. The hunt continues across a vast landscape of possibilities. Dark matter might be primordial black holes formed in the early universe. It might be composite particles in a hidden sector with its own forces and interactions. It might be something we haven't imagined yet. What's certain is that 5% of the universe is not enough. Somewhere in the darkness, most of reality waits to be found. For a few weeks each year, the LHC doesn't collide protons. Instead, beams of lead nuclei atoms stripped of their electrons, each containing 208 protons and neutrons, circle the ring and crash together at nearly light speed. The collisions release astonishing energy densities. For a fleeting moment, a tiny volume of space reaches temperatures exceeding 4 trillion degrees Celsius 250,000 times, hotter than the sun's core. At these temperatures, protons and neutrons melt. Their constituent quarks and gluons break free, creating a state of matter called quark-gluon plasma. CERN's ALICE experiment was designed specifically to study this primordial soup. Its detector surrounds the collision point, tracking thousands of particles that stream outward as the plasma cools and hadrons reform. The system captures 12 billion lead-lead collisions during each. Heavy ion run 40 times more than previous periods, building up statistical precision. Quark-gluon plasma filled the entire universe. During its first microsecond, everything was too hot for bound protons and neutrons to exist. Instead, quarks and gluons moved freely in an expanding fireball. As the universe cooled below about 2 trillion degrees, quarks condensed into hadrons in a phase transition called hadronization. ALICE recreates those conditions, studying how the transition occurs. How quarks and gluons behave when unconfined. The plasma behaves unexpectedly. Early predictions suggested it would be gas particles moving nearly independently, like air molecules. Instead, it flows like a liquid. Not just any liquid, Measurements of viscosity indicate quark-gluon plasma is the most perfect fluid ever observed. With viscosity to entropy ratio approaching the quantum mechanical minimum, it flows with almost no resistance, like a superfluid. This perfect liquid behavior reveals information about the strong force at high temperature. Quarks and gluons, even when no longer confined inside hadrons, remain strongly coupled. They interact vigorously, thermalizing almost instantly, flowing collectively rather than independently. The phenomenon challenges theoretical understanding and requires sophisticated simulations to explain. ALIC also studies how heavy quarks charm and beauty traverse the plasma. These massive quarks are produced early in the collision, then plow through the surrounding medium as it evolves. Their behavior provides a tomographic probe, analogous to how X-rays map internal structures. Measurements show the plasma is opaque to high-energy particles, suppressing jets and heavy quark production in a phenomenon called jet quenching. The Heavy Ion program explores not just the first microsecond of cosmic history, but the nature of the strong force under extreme conditions. Each collision creates a miniature Big Bang, lasting T-23 seconds, expanding and cooling until it freezes into ordinary hadrons. From those trillion-degree instants, physicists extract insights about how matter behaves when everything melts into its most fundamental components. The Higgs boson, discovered in 2012, couples to mass. Heavier particles interact with it more strongly. This means the Higgs decays most often to the heaviest particles energetically accessible. Bottom quark-antiquark pairs 58% of the time. W boson pairs 21%. Tau lepton pairs 6%. Charm quarks 3%, but the Higgs can also decay to second-generation particles, muons. The branching ratio is tiny, about 0.02%, or 1 Higgs in 5,000. For every Higgs decaying to muons at the LHC, 1,000 other processes produce muon pairs that mimic the signal. Finding this rare decay is like searching for specific grains of sand on a beach. Atlas and CMS announced first evidence for Higgs decays to muons in 2020. But evidence means 3 sigma suggestive but not definitive. By July 2025, with more run-3 data, Atlas reached for 0.3 sigma significance. The signal had strengthened, approaching the 5 sigma threshold that physicists require for claiming a discovery. Why do rare decays matter? Because they test the Higgs mechanism's predictions with precision. The standard model calculates exactly how often the Higgs should decay to each particle type. Based on those particles' masses, the muon branching ratio 0.0 to 19% derives from the muon's mass. Any deviation would signal new physics. The measurements also probe quantum loops. Virtual particles can affect decay rates through quantum corrections. New heavy particles, if they exist, would circulate in these loops even if too massive to produce directly. Their effects would show up as discrepancies between measured branching ratios and standard model predictions. The experimental challenge is formidable. Atlas and CMS analyze thousands of years' worth of equivalent collision time, though it accumulates in nanoseconds. Machine learning algorithms sift through petabytes of data, identifying events where two muons with the right combined mass might have come from a Higgs decay. Every variable, the muon's energies and angles, the presence of jets. Missing energy provides information that separates signal from background. The rarer the decay, the harder the measurement, but also the more sensitive to new physics. Atlas has also narrowed in on Higgs decays to a Z boson and a photon, with a branching ratio of 0.15%. CMS searches for decays to invisible particles, which would reveal if the Higgs couples to dark matter. These analyses transform the Higgs from a discovery into a precision instrument. Each measured branching ratio constrains the Higgs couplings, tests the standard model, searches for deviations that might point towards something deeper. The work requires patience, analyzing decades of data, reducing systematic uncertainties, coaxing signals from noise. But in those rare decays, where quantum mechanics operates at its most subtle, new physics might hide. Atlas is immense. 46 meters long, 25 meters in diameter, weighing 7,000 tons. It stands as the largest particle detector ever constructed. The entire apparatus surrounds a single point, the collision region where proton beams cross, where energy becomes matter, where physics happens. At last, the detector is built in layers, each designed to identify different particles. Closest to the collision point lies the inner tracker, silicon sensors covering 60 square meters, arranged in concentric cylinders and disks. When charged particles streak through, they ionize the silicon, creating microscopic electrical pulses. The system records these pulses with extraordinary precision, 10 micrometer resolution, allowing physicists to reconstruct particle trajectories and identify where they originated. A superconducting solenoid magnet surrounds the tracker, generating a 2 Tesla magnetic field. Charged particles curve in this field. Measuring the curvature reveals their momentum. The more energetic the particle, the straighter its path. Beyond the solenoid sits the calorimeter system, layers of metal, and scintillator that measure particle energies by complete absorption. Electrons and photons interact electromagnetically, showering into cascades of secondary particles. Hadrons penetrate deeper, creating hadronic showers. The calorimeters weigh 2,500 tons and operate with liquid argon cooled to -183 C. The outermost layer is the muon spectrometer. Only muons penetrate this far, everything else has been absorbed by the calorimeters. 3 massive toroidal magnets, each weighing 100 tons, bend muon trajectories. Chambers filled with gas detect the muon's passage, allowing precise momentum measurements independent of the inner tracker. CMS, the compact muon solenoid, takes a different approach to achieve similar goals. At 21.6 meters long, 14.6 meters in diameter, and 14,000 tons, it's smaller but denser than Atlas. The compact in its name refers to its design philosophy, a single enormous solenoid magnet. 13 meters long and 6 meters in diameter, generates a 3.8 Tesla field, nearly twice ATLAS's field strength. This intense magnetism allows precise momentum measurements in a smaller volume. Science directs calorimeters nest inside the solenoid unusual, since most detectors place magnets inside calorimeters. This requires the calorimeters to be compact and fast. The electromagnetic calorimeter uses 76,000 lead tungstate crystals, which scintillate when particles pass through. The hadronic calorimeter uses brass absorbers and plastic scintillators, reading out through 500,000 channels. Why do independent detectors? Redundancy and cross-checking. Atlas and CMS compete and collaborate simultaneously. When both see the same signal, as with the Higgs discovery, confidence soars. When one sees something the other doesn't, physicists know to be cautious. The collaborations share data and techniques but maintain independence, ensuring that systematic errors don't affect both experiments identically. Building these cathedrals of silicon and steel required international collaboration. Atlas involves 3,000 physicists from 181 institutions in 38 countries. CMS has similar numbers. The projects took 15 years to design and construct, incorporating technologies that didn't exist when planning began. They represent not just engineering achievements but monuments to cooperation, built particle detector by particle detector, component by component, by thousands of people working toward a common goal, understanding the universe. The LHC produces proton-proton collisions at a rate of 40 million per second. Each collision generates hundreds of particles, creating a flood of raw information that would fill thousands of DVDs every second. If recorded completely, it cannot be recorded completely. The physics lies buried under background ordinary processes, well-understood interactions. The mundane reality of particle physics. Higgs bosons appear once in every 10 billion collisions. New particles would be rarer still. Recording everything would mean drowning in irrelevant data. The trigger system makes split-second decisions about what to keep. Custom electronics examine each collision in microseconds, looking for interesting signatures, high-energy particles, unusual patterns, anything that might indicate rare physics. The system reduces 40 million collisions to about 1,000 per second, a factor of 40,000 compression, implemented in hardware before data ever reaches computers. CERN's surviving data flows to the worldwide LHC computing grid, a network of 170 computing centers across 40 countries. CERN serves as the Tier 0 hub, performing initial reconstruction and distributing data to 13 Tier 1 centers. These regional hubs connect to hundreds of Tier 2 university and laboratory facilities. The system distributes 30 petabytes of data annually, with 100,000 processor cores working continuously. Processing that data has transformed over the past decade. Machine learning has moved from experimental curiosity to essential tool. Neural networks trained on simulated collisions learn to identify particle types, reconstruct tracks, separate signal from background. These algorithms achieve performance impossible with traditional methods, operating at speeds necessary for real-time decisions. The trigger system itself increasingly relies on machine learning. Modern implementations use GPS graphics processors, originally designed for video games, to run neural networks fast enough. For real-time event selection, the hardware examines each collision event in microseconds, applying trained algorithms to spot potentially interesting physics. Analyzing the data to produce physics results takes months. Collaborations develop sophisticated statistical methods, estimate backgrounds, calculate systematic uncertainties. A single measurement, say the Higgs mass or a branching ratio, might require analyzing petabytes of data, running millions of simulated collisions for comparison, checking thousands of potential systematic effects. The computing challenges will intensify. The high-luminosity LHC, starting operations in 2029, will increase collision rates fivefold. Data volumes will grow proportionally. The experiments are developing new trigger algorithms, more efficient data formats, better compression techniques. Machine learning will become even more central, with AI systems performing tasks that currently require human physicist expertise. This infrastructure, hardware and software, algorithms and networks, distributed globally and operated continuously, represents a computing achievement comparable to the detectors themselves. The LHC produces data. The grid and its algorithms transform that data into physics. Every discovery emerges not just from particles colliding, but from millions of processor cores analyzing those collisions, guided by sophisticated algorithms that have learned what to look for in the chaos. At 3 a.m., the CERN control room glows with screens. Shift physicists sit at workstations monitoring systems, watching collision rates, checking detector status. The room feels calm despite the extreme physics happening underground. Proton beams carrying energy, equivalent to aircraft carriers moving at 99.9999991% light speed, circling 11,000 times per second through magnetic fields stronger than Earth's by 10,000 times. The shift coordinator scans displays showing the detector's vital signs. Pixel trackers report normal temperatures. Calorimeter voltages stable. Muon chambers operational. Trigger rates nominal. Everything appears green, which in the control room means working properly. Alarms sound occasionally, minor glitches, automatic systems correcting themselves, operators acknowledging warnings. Most problems resolve without intervention. The detectors contain thousands of subsystems, each monitored by sensors, each capable of generating alerts. Distinguishing routine anomalies from genuine problems requires experience. Sometimes things go wrong more seriously. Magnets quench sudden loss of superconductivity that releases stored energy as heat. The beam must be dumped instantly. 360 megajoules of protons steered into graphite absorbers kilometers away. Vacuum leaks require sealing. Cooling systems fail and need backup. Electronics overheat. Cables malfunction. The machine is complex enough that something always needs attention. Then there was the Weasel incident. In April 2016, a stone marten, often mistakenly called a weasel, chewed through an electrical cable outside an above-ground transformer station. The resulting short circuit shut down the entire accelerator complex. Engineers found the unfortunate animal's remains near a damaged 66 kilovolt transformer. The creature had managed to briefly halt the world's most powerful scientific instrument. NPR's incident became legend, spawning jokes about timeline shifts and alternate realities. More practically, it prompted improvements in wildlife protection systems. Nature occasionally intrudes on high-energy physics. In unexpected ways, most nights pass without drama. Data accumulates steadily. Collision by collision, event by event, the LHC writes information that will later be analyzed. Searched, questioned. The control room physicists maintain vigilance, ensuring the machine runs smoothly through the night while most of Europe sleeps, unaware that beneath them, particles collide at energies not seen since the universe's first moments. While Atlas and CMS pursue high-energy collisions head-on, LHCb points its detector down one of the beam lines at a slight angle, collecting particles that fly forward in the aftermath of collisions. This geometry optimizes it for a different mission, studying the decays of beauty quarks. Beauty quarks, also called bottom quarks, are the second heaviest quark flavor, with a mass about 4 times larger than protons. When created in LHC collisions, they live for picoseconds before decaying through the weak force into lighter quarks. Those decays follow specific patterns dictated by the CKM matrix, a 3x3 mathematical object that describes how quarks mix. CERN Courier CKM matrix contains one complex phase, a number involving the imaginary unit script -1. This complex phase is the only source of CP violation in the Standard Model's quark sector. It explains why matter and antimatter behave slightly differently, why certain decay processes occur at different rates for particles versus antiparticles. LHCb measures CP violation with extreme precision. The experiment collects billions of beauty hadron decays mesons like BO and B, baryons like B, and analyzes how their decay rates compare to those of their antimatter partners. Differences appear at the percent level or smaller, requiring enormous datasets and careful control of systematic effects. One crucial parameter is the angle gamma-gamma of the unitarity triangular geometric representation of the CKM matrix's internal consistency. Measuring gamma through multiple independent decay channels tests whether the Standard Model's description is self-consistent. Current measurements agree beautifully, determining gamma to within a few degrees. This precision constrains new physics scenarios and validates decades of theoretical development. LHCb also studies strange quarks lighter than beauty, longer-lived, but still heavy enough for interesting weak decays. Strange mesons called kaons exhibit subtle CP violations that were first observed in the 1960s. Modern measurements at LHCb achieve precisions that allow testing quantum mechanics itself, examining whether kaons violate Bell inequalities at the boundary between microscopic quantum behavior and macroscopic classical reality. The flavor frontier is about precision, not energy. While Atlas and CMS search for new heavy particles, LHCb looks for new physics indirectly. Through deviations in well-predicted processes, virtual heavy particles affect decay rates through quantum loops, even when they're too massive to produce directly. A new charged Higgs, a leptoquark, as boson any of these could subtly alter beauty quark decays. So far, the Standard Model passes every test. Each measurement of the CKM parameters confirms predictions. CP violation appears exactly where expected, with the magnitudes theory calculates. But every % of improved precision narrows the space where new physics could hide. And every rare decay measured adds another constraint. The strategy is patient and methodical. Measure everything measurable. Compare to predictions. Watch for discrepancies. Somewhere in the vast landscape of flavor physics, a crack in the Standard Model might emerge. The universe was once perfectly symmetric. In its earliest moments, when temperatures exceeded 100 billion degrees, no distinction existed between electromagnetic and weak nuclear forces. Photons and W and Z bosons were indistinguishable members of a unified electroweak force. Particles had no mass. The Higgs field sat at zero everywhere. As the universe expanded and cooled, it approached a critical temperature around Kelvin, about 1/1,000,000,000th of a second after the Big Bang. At this threshold, a phase transition occurred. The Higgs field underwent symmetry breaking, acquiring a non-zero value throughout space. This sudden change broke the electroweak symmetry, splitting the unified force into electromagnetism and the weak force. Particles coupled to the Higgs field acquired mass. Rxiv. Was this transition smooth or violent? In a crossover transition, the Higgs field gradually rises from zero to its final value, like water slowly becoming thicker as it cools toward freezing without forming ice. In a first-order transition, bubbles of broken symmetry nucleate and expand, like water suddenly crystallizing into ice. The bubbles collide, releasing energy, generating gravitational waves that might still ripple through space-time billions of years later. The nature of the electroweak phase transition depends on the Higgs boson's mass and its interactions with other particles. With the measured Higgs mass of 125 GeV, standard model calculations suggest the transition was a smooth crossover, no bubbles, no gravitational waves, just a gradual shift as the universe cooled. But beyond standard model physics could change the story. Additional Higgs bosons, new particles that interact with the Higgs field, modifications to the Higgs potential, any of these could make the transition first order. A violent electroweak phase transition would have profound implications. The expanding bubbles could create matter-antimatter asymmetry. Through a process called electroweak baryogenesis, particles passing through bubble walls would experience CP-violating interactions, preferentially producing matter over antimatter. This mechanism requires a first-order transition. The standard model's smooth crossover cannot generate sufficient baryon asymmetry. If the electroweak phase transition was indeed first-order, new physics beyond the standard model must exist. Gravitational wave observatories like LISA, planned for the 2030s, will search for the characteristic signals. A first-order phase transition in the early universe would produce a stochastic background of gravitational waves, a permanent humming of space-time at specific frequencies. Detection would reveal not just that the transition was violent, but also information about the energy scale and the new particles involved. LHC measurements constrain these scenarios. Precise determination of the Higgs boson's self-coupling, how strongly it interacts with itself, will test the shape of the Higgs potential. Searches for additional Higgs bosons continue. Every constraint on new physics narrows the parameter space for a first-order transition. The electroweak phase transition shaped our universe, whether it occurred smoothly or explosively, whether it generated matter-antimatter asymmetry, or left that mystery unexplained. These questions connect particle physics to cosmology, bridging the smallest scales with the largest, linking experiments at CERN to the fate of everything. Quantum chromodynamics, the theory of the strong force, contains a mystery. The equations permit a turn that would violate CP symmetry, causing neutrons to have measurable electric dipole moments. Experiments constrain this possibility severely. If the term exists, its coefficient must be smaller than 1 part in a billion. Why should a theoretically allowed term be so tiny? Nothing in the theory forbids it. Yet nature appears to have set this parameter to essentially zero with extraordinary precision. This is the strong CP problem. Strong CP problem, Wikipedia, 1977. Roberto Pache and Helen Quinn proposed an elegant solution, a new symmetry, that dynamically drives the problematic term to zero. Frank Wilczek and Steven Weinberg independently realized this symmetry predicts a new particle, the axion. Axions would be extraordinarily light, with masses ranging from microelectron volts to millielectron volts depending on. When the Pache-Quinn symmetry breaks, they would interact incredibly weakly with ordinary matter, coupling primarily to photons through an effective interaction that allows axions to convert into photons in strong magnetic fields. These properties make axions nearly invisible. They would pass through matter almost unimpeded, interacting rarely enough that detecting them requires dedicated experiments. Helioscopes search for axions produced in the Sun, attempting to convert them into X-rays using powerful magnets. Haloscopes look for dark matter axions in the Milky Way halo, resonating microwave cavities at specific frequencies where axion-to-photon conversion would occur. The dark matter connection elevates axion searches from solving an aesthetic problem to potentially explaining the universe's composition. If axions have the right mass, around 10 to 100 microelectron volts, they would have been produced abundantly in the early universe through vacuum misalignment. As the universe cooled below the QCD phase transition temperature, the axion field would have started oscillating, behaving like a collection of cold particles, dark matter. Multiple experiments hunt for axions across different mass ranges. ADMX in the United States scans systematically through frequencies, improving sensitivity year by year. CAST at CERN watches for solar axions. IAXO, planned for the next decade, will increase sensitivity thousandfold. If axions exist in the predicted mass range, these experiments should find them. The LHC contributes indirectly. Searches for exotic Higgs decays could reveal axion-like particles. Measurements of rare processes constrain models. The strong CP problem connects to the standard model's structure and its solution, whether through axions or some other mechanism, will reshape our understanding of the strong force and potentially illuminate dark matter's identity. The LHC will run through the 2020s, accumulating data, refining measurements, searching for subtle deviations. In 2029, it will shut down for a major upgrade to become the high luminosity LHC for short. So luminosity measures collision rate. Higher luminosity means more collisions per second, more data, better statistics for rare processes. The HLLHC will increase luminosity fivefold through upgraded magnets, new focusing systems, improved injector chains. The experiments will collect 10 times more data than the LHC's entire pre-upgrade operation. This flood of data will enable precision measurements impossible today. Rare Higgs decays will transition from evidence to discovery. The Higgs self-coupling, how strongly the Higgs boson interacts with itself, will be measured directly, testing the shape of the Higgs potential. Subtle deviations in top quark properties, W boson couplings, and flavor physics could reveal virtual effects of particles too heavy to produce directly. But what comes after HLLHC? Several proposals compete, each with different strengths. The Future Circular Collider FCC envisions a 100-kilometer ring tunnel encircling Geneva. The first stage, FCCE, would collide electrons and positrons at energies optimized for producing Z bosons, W bosons, Higgs bosons, and top quarks in vast quantities, a Higgs factory generating millions of Higgs bosons with extreme precision. The second stage, FCCHH, would collide protons at 100 TeV, 7 times the LHC's energy, directly producing particles up to tens of TeV masses. The FCC feasibility study concluded in 2024. Construction could begin in the 2040s if approved, with first collisions in the 2050s. The price tag, approximately €20 billion for the tunnel and initial electron-positron collider, with additional billions for the later proton-proton stage. China has proposed a similar two-stage facility. The Circular Electron-Positron Collider CEPC, followed by a proton collider. Japan considers the International Linear Collider ILC, a 30-kilometer straight-line electron-positron collider. Each project offers precision measurements and discovery potential at complementary energies. The muon collider concept has gained attention recently. Muons are 200 times heavier than electrons, allowing them to radiate far less energy when accelerated in circular rings. A compact muon collider could reach high energies in a relatively small facility. The challenge: muons decay in microseconds, requiring rapid acceleration and immediate collision before they disappear. CERN's and technical advances in magnet design and cooling techniques have revived interest. A muon collider could explore the 10 TeV scale in a ring smaller than the LHC's, complementing rather than competing with FCC. The European Strategy for Particle Physics update considers it as a possible post-HLLHC option. The global competition is also cooperation. CERN, Fermilab, Keck, IAGP laboratories worldwide share technologies, compare designs, train students together. Particle physics operates internationally because the questions transcend borders. The next major collider, wherever built, will involve physicists from dozens of countries, pooling expertise and resources toward common scientific goals. The future depends on discovery. If HLLHC finds clear signs of new physics-additional Higgs bosons, supersymmetric particles, unexpected signals, the case for more powerful machines strengthens. If the data shows only the standard model, precision measurements become paramount. Either path justifies next-generation colliders. But the specific design and energy scale might shift based on what LHC reveals. What if we find nothing? The LHC has exceeded design specifications. It discovered the Higgs boson at 125 GeV, completing the standard model. It has searched for supersymmetry, finding no evidence below several TeV. It has looked for extra dimensions, dark matter particles, new-gauge bosons, exotic Higgs decays, lepton flavor violation, and countless other signatures. The results consistently show the standard model working perfectly. This success creates discomfort. The standard model is incomplete. It doesn't explain dark matter, matter-antimatter asymmetry, neutrino masses, dark energy, quantum gravity. Yet within its domain of applicability, the model works with extraordinary precision. No cracks have appeared at the energy scale's LHC probes. The hierarchy problem exemplifies the concern. The Higgs mass should receive enormous quantum corrections from virtual particles, pushing it toward the Planck scale 1019 GeV unless something cancels these corrections. With extraordinary precision, supersymmetry provided a natural cancellation mechanism. Every standard model particle would have a superpartner, and their quantum corrections would cancel. But no superpartners have appeared at LHC energies. Without such mechanisms, the Higgs mass appears fine-tuned, delicately adjusted to the observed 125 GeV. Through a coincidental cancellation of huge numbers to 30 decimal places. Fine-tuning isn't logically impossible, but it violates physicists' aesthetic sense. Nature doesn't seem to require such precise adjustments elsewhere. Why here? One response invokes the multiverse. If an enormous, perhaps infinite number of universes exist with different fundamental constants, we necessarily inhabit one where the Higgs mass allows atoms, chemistry, and life. The anthropic principle: we observe what we must observe to exist as observers. Most universes have different Higgs masses. Those universes contain no beings asking why. This perspective troubles many physicists. It abandons the quest to explain why parameters take specific values. Replacing explanation with "it just is that way in our universe." Predictions become impossible. Any observation can be explained by anthropic reasoning. The scientific method requires testable hypotheses. The multiverse might be forever beyond experimental reach, yet particle physics continues. Even if no new particles exist below 10 TeV, precision measurements constrain higher scales through virtual effects. Rare decays probe quantum loops. Flavor physics tests the CKM matrix structure. Neutrino experiments explore mass generation. Gravitational waves might reveal cosmological phase transitions. Dark matter experiments pursue non-collider signatures. The nightmare scenario isn't actually a nightmare, it's just challenging. Physics would shift from discovery of new particles toward precision tests of the standard model and astrophysical observations. Theory would grapple with naturalness problems and quantum gravity. Progress would continue, perhaps differently than expected. But the questions remain profound regardless of what the LHC finds or doesn't find. We search anyway because we don't know what's there until we look. Every major discovery in history surprised someone. The universe has proven strange beyond imagination again and again. Assuming we've seen everything important at energies below 10 TeV would be hubris. The LHC runs, the detectors record, the analyses continue. And physicists remain alert for the unexpected because nature has never run out of surprises yet. Imagine the morning it happens. Not at a planned seminar, not after careful preparation, but during a routine data quality check. A graduate student, bleary-eyed from all-night analysis, notices something odd in a histogram. The distribution should be smooth background processes producing a gentle curve. But there's a bump, small but persistent, to standard deviations above expected, probably statistical fluctuation, probably nothing. She runs the analysis again with different selection criteria. The bump remains. She checks for software bugs. None found. She examines detector calibrations. Everything looks normal. The bump sits there at 3.2 TeV, refusing to disappear. By morning, 3 more analysts have independently noticed it. The analysis coordinator pulls up the plot at the weekly meeting. Anyone know what this is? Heads shake. Someone suggests it's fake data contamination. It isn't. Someone else proposes a pile-up artifact. Checks show it's not. The bump reaches 3 sigma within 2 weeks. Internal review committees convene. Every systematic uncertainty gets scrutinized. Background modeling is questioned, tested, refined. The signal persists. The collaboration establishes a task force to study the anomaly systematically. Other analyses start looking. If there's a real particle at 3.2 TeV, it should appear in multiple channels. Teams search for the object decaying to different final states: photon pairs, lepton pairs, jets. Missing energy. A faint excess appears in the diphoton channel. Another team sees something in 4 lepton events. Now it's serious. The experimental collaboration shares preliminary information with the other detectors team. Do you see anything at 3.2 TeV? Silence then. Let us look. A week later, we might have something. Very preliminary. Don't get excited yet. The rumors begin circulating. Talks at conferences carefully avoid the topic while everyone asks about it privately. Theorists start writing papers exploring what a 3.2 TeV resonance could be. An extended Higgs sector? AZ boson? A graviton from extra dimensions? Something completely unexpected? 6 months pass. The signal grows with more data. Both experiments now see it at 4 sigma. The collaborations prepare simultaneous papers. The internal review process is exhaustive. Every plot questioned, every assumption challenged, every systematic uncertainty evaluated from multiple angles. The papers are submitted on the same day. Seminars are scheduled at CERN and Fermilab. Press releases are prepared but held. Nothing is announced until the significance reaches 5 sigma in both experiments independently. The morning it reaches 5 sigma, the graduate student who first noticed the anomaly sits in the CERN auditorium, watching the official presentation. The spokesperson shows the plot now pristine, polished, publication ready. The bump is undeniable, a clear peak rising from background like a mountain from plains. Confidence level: 5 point to sigma at ATLAS, 5 point for sigma at CMS. The auditorium erupts in applause. Not celebration, not yet, but recognition of the moment's significance. Discovery doesn't mean understanding. Nobody knows yet what the particle is, what it does, why it exists. That will take years of additional measurements, spin determination, coupling measurements, production mechanisms, decay branching ratios. But the discovery itself is irrevocable. Nature contains structure at 3.2 TeV. The standard model is incomplete, not just philosophically, but experimentally. A new era begins. Physics changes forever, not in a single instant, but through gradual confirmation. The anomaly appears. Skepticism reigns. Evidence accumulates. Systematic studies eliminate alternative explanations. Both experiments confirm independently. The community reaches consensus. Papers are published. Theorists work to understand implications. Experimentalists design new measurements. A generation of PhD students will write theses analyzing the new particle's properties. The morning it happens is quiet and ordinary, starting with a graduate student noticing an unexpected histogram feature. The revolution begins with a careful question. What is this? From that question flows everything else: the verification, the confirmation, the discovery, the understanding that will reshape physics. The universe reveals another secret, and patient, systematic investigation transforms observation into knowledge, one measurement at a time. And so we come to the end of our journey, cosmic travelers. We've descended 17 miles beneath the surface, into a tunnel carved through ancient rock and clay. We've watched protons accelerate to speeds where time itself slows down. We've witnessed collisions hotter than any star, colder than the space between galaxies. We've met the Higgs boson at matter, exotic particles that exist for less than a trillionth of a second. We've explored the mysteries that remain: dark matter, vacuum stability, The matter-antimatter asymmetry. The Large Hadron Collider is more than a machine. It's a monument to human curiosity, to the desire to understand, to the refusal to accept ignorance when knowledge is possible. Thousands of people from over 70 countries have worked together to build it, to operate it, to analyze the data it produces. They speak different languages, they come from different cultures, but they share one obsession: to know what the universe is made of at its most fundamental level. And they're succeeding. Every measurement constrains the possibilities. Every discovery reveals a new layer of reality. Every null result eliminates a theory and sharpens our focus. The standard model has survived test after test, matching predictions with stunning precision. But cracks are appearing. Anomalies hint at physics beyond what we know. The absence of dark matter particles suggests we've been looking in the wrong places. Or in the right places, but at the wrong energies. The next discovery could come at any moment. A graduate student checking plots might see a bump where no bump should be. An automated analysis might flag an event too strange to be background. A combination of measurements might suddenly reveal a pattern that no one expected. Or the discovery might take decades more. Science is patient. The universe doesn't reveal its secrets on our schedule. But whether the breakthrough comes tomorrow or 50 years from now, the search continues. The high luminosity upgrade will increase the LHC's power. The future circular collider, if built, will probe even higher energies. Won't colliders, neutrino experiments, dark matter detectors all push forward on different fronts, mapping the territory of the unknown. We don't know what the universe is hiding, but we know it's hiding something. The standard model leaves too many questions unanswered. Dark matter exists but remains invisible. Dark energy accelerates the universe's expansion but has no explanation. The matter-antimatter asymmetry demands new physics. The vacuum might be stable or metastable, and we don't yet know which. These aren't abstract puzzles for physicists alone. They're questions about the nature of reality itself. Why does anything exist? Why these laws and not others? What came before the Big Bang, if anything? Is our universe the only one, or one of countless others in an infinite multiverse? The LHC can't answer all these questions, but it can answer some, and each answer leads to new questions, deeper mysteries, broader horizons. Thank you for joining us tonight on the Cosmic Atlas. If this journey sparked something in you, curiosity, wonder, a sense of connection to the universe, please consider subscribing. We create these explorations regularly, diving into the mysteries of space, time, matter, and energy. Your support helps us continue. If you enjoyed this, hit the like button. Share it with someone you think might find it fascinating. Leave a comment if you have thoughts or questions. We love hearing from you. And as you drift off to sleep tonight, remember this: 17 miles beneath the border of Switzerland and France, protons are still circling, collisions are still happening, data is still accumulating, and somewhere in that data, hidden in the numbers and the graphs and the measurements, might be the answer to a question humanity has asked since the first time someone looked up at the stars and wondered, what is everything made of? Why does anything exist? And what secrets is the universe still keeping from us? The search continues. The machines keep running. The scientists keep analyzing, and one day, perhaps soon, we'll find the crack, the tiny fracture in the equations that opens the door to something entirely new. Until then, rest well, cosmic travelers. The universe is vast, ancient, and strange, but we're learning to read its language, one particle at a time. Thank you for exploring with the Cosmic Atlas. Sleep peacefully and dream of the mysteries waiting to be discovered.